Welcome back to History of Mathematics. This is our third video, and we are moving on to Chapter 2 of Stuart Hollingdale's book, Makers of Mathematics, which focuses on classical Greek mathematics. I thought I would give you a timeline of the various civilizations that we've talked about so far. So the focus on Chapter 1 was the mathematics of ancient Egypt, and as mentioned in the book, the civilization that we refer to as ancient Egypt lasted from roughly 5000 BC to 100 BC. Now, the classical Greek civilization that we will be talking about in this video lasts from 600 to 300 BC. There are several features that distinguish the mathematics of classical Greece from the mathematics of Egypt. One of them is abstraction, and another is insistence on deductive proofs. As we saw with our work on problems from the Alms Papyrus, the work of the ancient Egyptian mathematics was focused on examples, specific examples. So we don't have any record of dealing with abstraction, and we don't have any record of an insistence on deductive proofs. Another feature that we'll discuss in a later video is classical Greek mathematics shifts focus from arithmetic and algebra that we saw in the problems covered in the Alms Papyrus. It shifts focus to geometry. And certainly a notable group during the classical Greek period was the Pythagoreans. So Pythagoras of Samos founded a school of philosophy and mathematics. Most people know the name because of their famous theorem, but the focus of the school was on whole numbers and their properties. The Pythagoreans felt that the universe could be described in terms of whole numbers and their properties. Now, since Greek mathematics focuses on deductive proofs, I thought it would be a good idea to contrast that with a different type of reasoning, inductive reasoning. So a deductive proof starts with established general principles and then proceeds to a specific conclusion. So deductive reasoning goes from general to specific, basically. Whereas inductive reasoning starts with specific examples, and then we try to generalize from those specific examples. So, as mentioned in Makers of Mathematics, the classical Greeks, in particular the Pythagoreans, were focused on properties of whole numbers. Now, in modern mathematics, we have a very useful technique for dealing with claims that involve properties of whole numbers, and that is called mathematical induction. It's kind of unfortunate that the technique is named that. Mathematical induction is in fact a deductive method of reasoning used to prove statements like this. So this is a claim mentioned in the book. So the claim is that whenever we add up a sequence of consecutive odd numbers, we will get a square. So if we add up the first two odd numbers, 1 plus 3, we get 2 squared. If we add up the first three odd numbers, 1 plus 3 plus 5 is 9. The sum of the first three odd numbers is 3 squared. the sum of the first 4 odd numbers, 1 plus 3 plus 7 is 16. If we add up the first 4 odd numbers, we get 4 squared. So this claim is saying that no matter what natural number n we use, if we add up the first n odd numbers, we will get n squared. So this is a claim that is especially nice to prove with mathematical induction. So let me review the technique of mathematical induction for you. You start with a base case. And we typically take n equals 1 as our base case. So if we add up the first odd number, we get 1 squared. Okay, so the base case shows the claim is true for a particular number. Now, once the base case is established, we move on to what I like to call the inductive hypothesis. And what we're going to do in the inductive hypothesis, we are going to suppose that the statement I'm writing down right now, we're going to suppose that this is true. For some fixed but unknown k. So we're going to suppose that is true. And now what we're going to do is we are going to examine the logical consequences of this inductive hypothesis. So this is what most people call the induction step. Okay, so what we're going to do is we are going to examine this expression. And the expression that I'm going to examine is this. 1 plus 3 plus 5 plus, we continue in that way, 2k minus 1. And I'm going to go ahead and add in the next odd number, which would be 2k plus 1. Okay. Now, I want to see what we can infer about this expression using this as a basis. Well, this equality says that whenever I have the sum of odd numbers up to this one, I can replace that with k squared. So this first bunch of terms can be replaced by k squared. Now I can't do anything with this yet, that's just kind of hanging around. Okay. But of course I do know from algebra that this trinomial here, this can be factored. I'm looking at that and I'm seeing, okay, well, that is equal to k plus 1 quantity squared. Now, this is actually an important feature of mathematical induction right here. So what we have just established is that if our claim is true for some natural number k, then it automatically holds for the next natural number, because we just showed that the sum of the first k plus 1 odd numbers must be equal to k plus 1 squared right here. Now that's if this is true. Now this interacts with the base case that we established over here. Okay, we established that the claim is in fact true for n equals 1. And this induction step says that whenever your claim is true for some natural number, it's true for the next one. So the fact that our claim is true for n equals 1 combined with this means that our claim is true for n equals 2. And the fact that the claim is true for n equals 2, combined with this, means that the claim is true for n equals 3. And the fact that the claim is true for n equals 3, combined with this, implies that the claim is true for n equals 4, and so on down the line. So we can keep on going and going there. So this technique allows us to prove that our original claim up here will hold no matter what value of n we want to use. So it's a very neat method for proving claims about natural numbers, the technique of mathematical induction.